This flick will continue discussing the previous chapter on mass and energy analysis of control volumes, but focusing on flow work and energy analysis of steady flow systems. First, we will learn about flow work and the energy of a flowing fluid. Some work is required to push the mass into or out of the control volume. This work is known as the flow work or flow energy, and it is necessary for maintaining a continuous flow through a control volume. To obtain a relation for flow work, consider a fluid element of volume V as illustrated here. Pretend the fluid immediately upstream as an imaginary piston that forces this fluid element to enter the control volume. The fluid element can be chosen to be sufficiently small so that it has uniform properties throughout. If the fluid pressure is P and the cross-sectional area of the fluid element is A, the force applied to the fluid element by the imaginary piston becomes P times A. This force must act through a distance L to push the entire fluid element into the control volume. Thus, the work done in pushing the fluid element across the boundary, or in other terms is the flow work, is equal to P times V. The flow work relation is the same whether the fluid is pushed into or out of the control volume. Now let us learn how to estimate the total energy of a flowing fluid. The flowing fluid's total energy consists of flow energy, kinetic energy, internal energy, and potential energy. On a unit mass basis, denoted by theta, it is presented as in the given form. As we already know, the combination of PV plus U equals the enthalpy H, so the relation reduces to the following manner. Many engineering devices such as turbines, compressors, and nozzles operate for long periods under the same conditions once the short startup period is completed. Steady operation is established and they are classified as steady flow devices. Processes involving such devices can be represented as an idealized process called the steady flow process. During a steady flow process, no intensive or extensive properties within the control volume change with time. Thus, the volume V, the mass M, and the total energy content E of the control volume remain constant. As a result, the total mass or energy entering the control volume must be equal to the total mass or energy leaving it. These observations greatly simplify the analysis. During a steady flow process, a control volume's total energy content remains constant. Thus, the change in the control volume's total energy is zero. Therefore, the amount of energy entering a control volume in all forms by heat, work, and mass must be equal to the amount of energy leaving it. Then, the rating form of the general energy balance reduces for a steady flow process to the following manner. The energy can be transferred by heat, work, and mass only. The energy balance in the latest equation for a general steady flow system can also be written as follows. And a more explicit and comprehensive expression is as in the given form. Consider, for example, a standard electric hot water heater under steady operation, as shown in a given illustration. A cold water stream with a mass flow rate m dot is continuously flowing into the water heater at state 1. A hot water stream of the same mass flow rate is continuously flowing out of it at state 2. The water heater is losing heat to the surrounding at a rate of Q dot out. The electric heating element supplies electrical work to the water at a rate of W dot in. We can say that the water stream experiences an increase in its total energy as it flows through the water heater, that is equal to the electric energy supplied to the water minus the heat losses. During this process, no work is done by the control volume and heat is supplied into the control volume. Therefore, both terms can be cancelled out from the equation. When performing a general analytical study or solving a problem involving an unknown heat or work interaction, we need to assume a direction for the heat or work interactions. In such cases, it is common practice to assume heat to be transferred into the system as a heat input at a rate of Q dot. Work produced by the system as a work output at the rate of W dot. Obtaining a negative quantity for Q dot or W dot simply means that the assumed direction is wrong and should be reversed. For single stream devices, the steady flow energy balance equation becomes the following expression. Dividing the latest equation by m dot yields the energy balance on a unit mass basis. Suppose the changes in the fluid's kinetic and potential energies are negligible. In that case, the energy balance equation is reduced further in the following manner. Many engineering devices operate essentially under the same conditions for long periods. Therefore, I will explain how to analyze energy interactions associated with various steady flow devices. First, let us consider nozzles and diffusers. A nozzle is a device that increases the velocity of a fluid at the expense of pressure. A diffuser is a device that increases the pressure of a fluid by slowing it down. That is, nozzles and diffusers perform opposite tasks. The cross-sectional area of a nozzle decreases in the flow direction for subsonic flows and increases supersonic flows. The reverse is true for diffusers. The heat transfer rate between the fluid flowing through a nozzle or a diffuser and the surroundings is usually very, very low. Therefore, Q dot equals 0 since the fluid has high velocities. Nozzles and diffusers typically involve no work, and any change in potential energy is negligible. But nozzles and diffusers usually involve very high velocities. Therefore, the kinetic energy changes must be included in analyzing the flow through these devices. Let us discuss the following example to comprehend the topic further. Based on this example, air enters the diffuser of a jet engine steadily at a specified velocity. The mass flow rate of air and the temperature at the diffuser exit are to be determined. Before we solve the problem, we must first specify our assumptions to simplify the analysis. The assumptions are presented here. We must first determine all the related states of air using the given information and establish the equations to be used to determine all the specified problems. The diffuser is taken as the control volume since mass crosses the system boundary during the process. The system has only one inlet and one exit. The inlet area of the diffuser is 0.4 square meters. The air leaves the diffuser with a velocity that is very small compared with the inlet velocity. State 1 represents the inlet of the control volume and state 2 as the outlet, and thus m dot is equal to m dot 1 equals m dot 2. For step 1, we begin by determining air properties at state 1 using the available information. The gas initial volume, pressure, and temperature have been provided as shown. Those properties represent state 1. As demonstrated, the mass flow rate at state 1 can be determined through the ideal gas equation of state. Through this exercise, we have successfully answered the first question, that is, to determine the mass flow rate of air. To determine the air properties at state 2, we will use the energy balance for this control volume under steady state conditions in the rate form as presented. Since the rate of change in the total energy equals 0, the expression reduces to the following terms. We know that the diffuser does not involve any work and heat interactions. Thus, those terms can be eliminated from the equation, becomes the following expression. And we solve for H2. Becomes the following manner. Usually, the outlet velocity is small compared with the inlet velocity. Thus, the kinetic energy at the exit can be neglected. This example demonstrates another technique of determining the enthalpy of air using table A17. Based on this table, the corresponding enthalpy of air at the diffuser inlet at 10 degrees Celsius or 283 kelvins is between a temperature of 280 and 285 kelvins. By performing the interpolation technique as described in the previous video, enthalpy at state 1 is 283.14 kJ per kilogram. Substituting H1 value into the latest equation, H2 equals 304.14 kJ per kilogram. Based on table A17, the corresponding air temperature of H2 lies between 300 and 305 kelvins. The interpolation technique is used to determine the diffuser outlet's air temperature, which is 303 Kelvin. Based on the first step, all the specified problems have also been solved at the same time.